Thank you very much, Ashur, for this kind introduction. Thank you for inviting me. So it's an honor for me. And as you can see, I'm going to talk today about X-ray spectroscopy, a very general framework. So, but in particular about transition metal complexes. So that's why I have put here the structure of a prototypical transition metal complex to illustrate the structure of my talk. And here you can see, okay, let's see. Yeah, so here you can see the plan for the talk. I will start from the introduction to the X-ray spectroscopy, very general, to the highly excited states and how we can calculate them with theoretical methods. So then give very brief introduction to transition metal chemistry and theory, and then talk about different types of spectroscopies and dynamics. So and to start with, I would like just to mention the classical X-ray field. So as you know, X-rays short wave electromagnetic radiation, where the wavelength is of order of 10 to 10 to the minus 3 nanometers. So this means that the wavelength is comparable to the size of molecules and atoms, or even smaller. So that's why it has a better spatial resolution than visible or ultraviolet light. So, and in general, one speaks about energies higher than 100 electron volts. And I mostly have been studying the systems and processes using soft X-rays. So it's from 100 electron volts to 100 kilo electron volts. And this classical X-ray science has been acknowledged already by the scientific community. Of course, the seminal event in science was the discovery of X-rays by Röntgen, and he has got the first Nobel Prize in this area. And then many other scientists have got also prizes due to deciphering the structures of different substances like crystals, macromolecules, DNA, and further biomolecular systems. So naturally, X-ray X-ray spectroscopy or X-ray analytical methods, they are associated with X-ray diffraction, so with studies of the structures. The arrangement of atoms within matter. But what I'm going to talk about today is spectroscopy, so not diffraction, and it has also been acknowledged by several Nobel Prizes. So and I hope there are more to come. And nowadays, so the spectroscopy, so when we resolve different signals in energies, so they appear to be very useful tools to study both geometrical and electronic structure of matter. So this is our current subject, but X-rays are also acknowledged not only in structural or natural sciences as such, but also in astronomy. So there was no place to put it. So there is also a physics Nobel Prize this year. So, which has been awarded for ultra-short pulses, which can also be easily generated or relatively easily generated in X-ray domain. So, but I will cover this matter slightly later. So, what's very specific about this X-ray spectroscopies if compared to usual ultraviolet or visible one? First of all, of course, it's element specificity. So if we look at the binding energies of core electrons of different elements, even those which are close in the periodic table to each other, we can see that the difference in this binding energy and electron volts is very substantial. So, and for transition metals and for other even more heavier elements, so they might reach 100 electron volts or even more, the difference between different elements. And taking into account that the resolution is usually better than 0.1 eV, so the difference in 100 eV, so it's huge. So one can resolve very many details about electronic structure. Another peculiarity is that in contrast to UV spectroscopy, we here describe transitions from localized core levels of some type of atoms to delocalized molecular orbitals, is shown here. And due to this locality of core orbitals, we probed local electronic structure of particular type of atoms embedded in their chemical environment. So a classical example, so also for which the Nobel Prize to Zygmunt was awarded, is this tetrafluoroacetate, ethyl tetrafluoroacetate molecule. So where it was first shown that different types of carbon atoms here having different chemical environments, they have substantially different chemical shifts, that one can resolve signals from these different carbon atoms. And of course, study how they change during chemical reactions and so on. So why I like soft X-ray spectroscopy in comparison to hard X-ray, as of course that it's easier in terms that the transitions, they are of dipole nature. So there are relatively strict dipole selection rules. So we don't need to take into account like quadrupole, magnetic dipole, and higher multipole terms, which one has to take into account for hard X-rays. And one peculiarity is also that if we are dealing with excitation or ionization of electron from L, M, or higher shells, so this means like from 2p orbitals or from 3d orbitals, 4f or 4d, so then one has to take into account strong spin-orbit coupling. So because without it, so one can't reproduce the results very well. And it's more like from dynamical viewpoint or from experimental viewpoint, this highly excited states, which we access by X-ray excitation, so they are very short-living. So we are kind of displacing our system very far from equilibrium, and that's why it tries to return as soon as possible into the ground state, into the equilibrium. That's why the lifetime of the core hole, which is left behind after excitation or ionization, it's usually of order or even shorter than 10 femtoseconds. So this gives rise to the so-called core hole clock method. So when we can see with X-ray spectroscopies on the processes which happen on this time scale of its lifetime. So another point which I would like to mention, so how the absorption spectrum looks like. So if we measure absorption and dependence of photon energy, okay, in this case hard X-ray, this doesn't matter. So one sees a sharp edge here, rising edge, so-called white line. That's why we are talking about edges in X-ray spectroscopy. So that's why one can say so that here we see edge energies of carbon, nitrogen, oxygen, and so on. And after that, so there is some more diffuse structure, which is called fine structure or XFS structure. And it's more related to the geometrical arrangement of atoms because it corresponds already to ionized electron when X-ray kicks out an electron from the molecule. And this electron wave coming from a particular atom is scattered from neighboring atoms, and due to interference of this direct wave and scattered wave, there are some modulations and absorption coefficients, so which we can see here. But this is more structural thing, more related to electron diffraction. But what I'm going to talk about now, so is this small feature, tiny feature, which is called pre-edge. So although it appears to be very tiny here, so it's not indeed. So it has quite strong intensity, so it can be easily detected, and it corresponds usually to the excitation from core orbitals to valence bound orbitals. So we are not usually ionizing electron. So, and despite of its smallness on this graph, so it contains plenty of information about electronic structure, as I will demonstrate to you. But you have noticed that in previous slides I mentioned classic X-rays. So classic means that there is something more modern, novel, and indeed there is. And let me just illustrate this, how this transition has happened. Probably you have noticed from literature or just communication with colleagues that there is a very much interest in X-ray spectroscopy right now. So there is a avalanche-like growth of number of spectroscopic studies, especially those ultra-fast ones, where like photochemistry or photophysics are studied. And this has been available or became possible due to invent of new X-ray sources. And actually, every new X-ray source has been a revolution in science. Again, let me mention the discovery of X-ray tubes and X-rays as such. So this was a tremendous revolution. So the next revolution happened like almost, well, let's say 70, 80 years later, when third generation synchrotrons were established. And one can say that even now, the lion's share of studies, spectroscopic studies are done at synchrotrons. So just because they were highly stable, widely tunable sources with high flux of X-rays. So it was needed for structural and spectroscopic studies. But later, in 90s, so people started to think and establish even newer types of sources, so-called free electron lasers, where relativistic electrons, due to oscillations in the periodic magnetic field, due to Bremsstrahlung, so they emit light, and since electrons are traveling very fast, so they travel together with light, and that's why light stimulates stimulated emission. So that's why they are called lasers. So although there is no classical lasing medium here, just a cloud of electrons is a lasing medium. So one talks about free electron lasers. And the peculiarity of the sources is that they are extremely brilliant. So they are so brilliant so that one shot of X-ray light so destroys the sample. And this allows to study different spectroscopic signals which are dependent on intensity, so like nonlinear signals. So there are some problems with the duration of such pulses. It was very difficult and took quite long to decrease the duration of pulses below 1 femtosecond, so to going into attosecond domain. But there is also another type of sources. So this is exactly the topic which has got attention from the Nobel Prize committee this year. So this, Nobel Prize in Physics 2023. So it's for high harmonic generation. So it's a process when one almost ionizes an electron with a field, but with a strong field. But the field, due to its oscillations, drives electron back to the target, electron recollides and emits a photon again. And this is a highly nonlinear process, and we see here up conversion. So the tiny laser energy, so they are summed multiple times up, and that's why we obtain pulse with much larger energy. So we are starting from usually infrared, and we are going up to soft X-ray domain with the source. And its peculiarity is that it's tabletop. It's not like free electron lasers, which are many kilometers in size. So it's a huge facility. High harmonic generation is a tabletop thing. And very distinct peculiarity of it is that one can generate extremely short, unprecedentedly short pulses of order of a few tenths of attoseconds. So, and with this one approaches the electron dynamics on its natural time scale. So nuclei are moving like on the time scale of probably hundreds of femtoseconds on average, but electrons are moving on attosecond time scale, and one can address this with types of spectroscopies. But of course, the progress in this field was not only due to an invent of new light sources. There are also a lot of work spent on X-ray optical devices, because one cannot just reflect X-rays as usual light, or focus it, or diffract. So, and of course, the spectroscopy as such has become possible due to these developments. And also sample preparation is one of the fields which contributed to the success, because soft X-rays, they require vacuum conditions, and it's very difficult to study something else apart from solids under vacuum conditions. So like liquids and gases are excluded, but due to invent of or establishment of liquid microjets or flat jets, one can nowadays also study solutions, gases, and so on. And most of the studies, joint experimental theoretical studies, which I will show you today, so they have been performed in solution, using these liquid microjets. Okay, so this means that when transferring from classical X-rays to novel ones, we can obtain access to processes which have not been available before, so which have been covered by our insufficient time resolution. So, and with this, one can see here, so there are two graphs. On one, on the left one, you can see time in femtoseconds. So this is this region below 1 femtosecond. So this is what we are just accessing right now, or since few years. So, and we are talking about photon energies in this range. So one can observe like charge migration. One can observe how exactly, when the molecule is ionized, how exactly electron is leaving the molecule, what does happen with other electrons, so how they correlate with each other, and so on. So one can study shake-up processes, for example, during ionization. So this is very, very fascinating, I think. And if we look at the right graph, you see here the intensity, so the amount of photons per pulse, and one can see that we can reach very high intensities. And I hope one day there will be a routine, so the X-ray multidimensional spectroscopies, nonlinear spectroscopies, will be routinely applied to chemical and physical samples. But it's yet a bit ambitious goal, so scientists are working on it. But let's look now from theoretical viewpoint. So what we are talking about. There are nowadays a lot of theoretical methods which can be used to study these highly excited states. And the main difficulty there is that they are really, really highly excited. So from viewpoint of theory, very, very formal theory, or excited states are not any different from any other electronic states. So they are just in between ground state and this first core excited state of interest. There are myriads of states which we are not interested in. So, and we need to somehow exclude them from consideration to make our problem feasible. So, in other words, for example, in absorption, we need to do the so-called covalent separation. This means that if we would like to excite an electron from core orbital to some empty molecular orbital, we should somehow omit excitations of electrons from high-lying molecular orbitals, which give rise to this uninteresting electronic states. So, and there are different ways to do this covalent separation, and there is a zoo of methods. You can see here a bunch of abbreviations, and I tried to classify this, to bring some order into the zoo according to 3 criteria. So one criterion is whether the method is single or multi-reference. So whether it's based on a single electronic configuration, or many or several electronic configurations can contribute with comparable weights to the wave function. So whether the orbitals are optimized or not optimized. That's why self-consistent field types of methods on non-self-consistent types of methods. And whether we are solving stationary Schrödinger equation or time-dependent Schrödinger equation. So this means that the method is formulated in time or frequency domain. So yeah, here we see this 8 groups, okay, essentially 7, because I don't know methods which belong to this group G. Today I would like to talk briefly about methods which are based on multi-configuration and self-consistent field theory. So this kind of multi-reference methods. And if we would like to study dynamics, so we go for explicitly time-dependent method. And in our case, the method of choice is time-dependent configuration interaction, which is also based on this MCSCF orbitals and wave functions. Yeah, just a very quick reminder, this MCSCF, multi-configurational SCF methods, so they are a hybrid of Hartree-Fock when we optimize orbitals. So we are changing them with some exponential operator, unitary operator. And configuration interaction when we decompose our wave function in multiple configurations and optimize energies with respect to these weights of these configurations. So in MCSCF, we do both. On the one hand side, it makes the method very expensive. On the other hand, it's quite accurate, quite flexible, and it's systematically improvable up to exact limit. One can also use on top of it like perturbation theory or multi-reference CI to account for correlation. It has no problems with charge transfer states like TDDFT does. So it might be crucial for excited states. Yeah, so there is one kind of problem here that one has to choose physical or chemically motivated or make a physical or chemically motivated choice of configurations. So, and I will come to this a bit later on the next slide. So, and finally, I mentioned strong spin-orbit coupling. In our case, we work in the so-called, how atomic physicists call it, LS coupling limit. So we compute states of different spins of different multiplicities separately. So, and then we mix them with some coefficients. And this mixing is due to spin-orbit coupling. So here is one more time how this MCSCF is doing core valence separation. So remember this myriads of states which I mentioned before, and to obtain all the states and their properties, we need to diagonalize Hamiltonian matrix. This Hamiltonian matrix has many billions times many billions, whatever trillions configurations, and we need to diagonalize it. This is not feasible. But in MCSCF, we usually rely on the so-called active space. We select a subspace of orbitals and allow excitations between them, whereas excitations from some other orbitals, they are forbidden. And we do only describe them only on Hartree-Fock level. We can use this trick for our good. We can put core orbitals here, like this is, it's difficult to see. So it's a iron pentacarbonyl complex. So we can put here, so this very tiny core orbitals into the active space. We can put everything what contains substantial contribution from 3D orbitals, because it's 2p to 3d, so this is a dipole allowed transition. So, and with this, if we can keep this active space stable, we solve the problem. So we will have only some fraction of valence orbitals, valence states, sorry, with this excitation from these ones to these ones, but a little fraction. And we will have also states where we excite from core orbitals to this d orbitals. So this means that we will reduce this huge Hamiltonian matrix to a much smaller submatrices. So this blue one for valence states, so this red excitations, or this smaller also blue one for core excited states. And These matrices are usually of a feasible size, so we can diagonalize them and obtain our states. So to mention is that nowadays many codes, quantum chemistry codes, can study four-excited states of X-ray spectra. Our developments are going in the direction of open MOLCAS program package, so it's a community-driven open source software. So if you would like to try it, so you are very welcome to download and install it. And many tools to study this different X-ray types of spectroscopy. So they are already implemented in open MOLCAS. Some of them are as a standalone programs, which are interfaced to open MOLCAS. Some of them are directly implemented into it. So, and with this procedure, which I described below, and we just limit the states by selecting an active space, we can calculate up to several tens of thousands of electronic states. And we do this usually for some fraction of valence states, low-lying valence excited states, highly lying core excited states, for like systems like neutral, when one electron is lost, two electrons are lost, so singly, doubly ionized systems. And then having these states and some properties of them, so we can describe just absorption when we excite to the state, so-called resonant inelastic X-ray scattering. So it's kind of an electronic analog of vibrational Raman spectra. So when we excite to some electronic state, so we end up in much lower electronic state. So we can also describe transitions from different charge manifolds. So if we ionize an electron flies out from a system, so then we end up in ionized states. And this gives us access to full XPS, so X-ray photoelectron spectra, or how it's called here, photoelectron spectrum test, or Auger electron spectrum, and so on. But this is all static spectra. They are often enough to interpret various kinds of spectroscopic signals. But what is important, so that this experimental pulses, they can be very short, and this means that they are very short in time, they are very broad in frequency domain. And with these pulses, one can involve many states, up to hundreds of states, into this excitation, prepare a complex superposition of the states. And this superposition will evolve in time also on a time scale of attoseconds, or probably a few femtoseconds. So one can study this electron dynamics, what I will also briefly touch. Yeah, so this is about general methodology, how to deal with this core excited states. As I mentioned, main types of systems which we have studied are based on transition metals. So, yeah, I wanted to mention. So I made this distinguished between static spectra and dynamic ones, time resolved ones. So this is kind of also a substructure of my talk. So I will talk also about frequency domain methods and time domain methods. So, and about transition metals, very briefly, since you all know all this, so just to make a proper context. As you know, the properties of these transition metals are determined by a partially filled D shell, and they are frontier, so they are balanced. They are involved in forming chemical bonds, and one can make different kinds of bonds, starting from almost purely ionic to covalent one. And upon this bonding, the orbital splits in the ligand field, and when we fill them with electrons, with a given number of electrons, we can follow different spin coupling patterns. We can obtain singlet state, triplet, or quintet, and so on. So this means that our transition metal has a magnetic moment, which we have to account for. Kind of formally depicted here as an arrow. But in addition to this, we have ligands, and they have also empty orbitals and filled orbitals, and that's why we have to account for ligand to metal charge transfer states and from metal to ligand charge transfer states. And if we shine light on this very complicated system, so we have states of different spin, of different nature, like ionic, covalently bound, and so on. So we can trigger many intricate processes which can be used, for example, in transformation of light, absorption of light, and transformation of it into electrical power or chemical energy, and so on. So like light harvesting devices and photocatalysis, and many more. So light emitting devices as well. And of course, we can use light not only to trigger these processes, but also to study using spectroscopy. So, and this is exactly what we briefly discussed before the talk began. So that spectroscopic signals are often very complicated, and one has to involve theory to decipher them, to interpret them. And this is where theory stands out, of course. So, but from the viewpoint of theory, transition metal complexes are not that easy. First of all, because we know that the electrons are highly correlated. So this means that sometimes even in the ground state, our wave function cannot be represented as a single configuration. We need multiple of them, so we need to apply multi-reference methods. But we also need to describe highly excited states of different multiplicity, of different nature, like charge transfer, metal-centered, ligand-centered transitions on a similar footing, so with similar level of accuracy. And this puts actually quite high demands on the theoretical method. So it's not that easy. And of course, the size of transition metal complexes. So here I just described the smaller ones here, but they can be much larger. Like in biological systems. So there are quite a lot of requirements to theoretical method here. Very briefly, so what kind of systems have we studied in our work? So these are model compounds, like this highly symmetric, smaller complexes, where we can test different things, where we can even kind of challenge or question some of the fundamentals of coordination chemistry as we have learned it during university studies, or view it under a different angle. So, but of course, not only these ones, there are like other classes of molecules, for example, those containing iodine, which are very important as model compounds. Iodine is very popular among ultra-fast scientists, is because it has a very giant dipole resonance in extreme ultraviolet domain, so on the border to X-rays. And this is very convenient to study it experimentally. But also we have studied functional complexes, like those, for example, which we have studied together with Professor Hilal and Mahmoud Abdel-Latif. So those which I used, where's my mouse? Can't see it. Yeah. So like these complexes, these ones which are used for photocatalytic water splitting, posed on a hydrogen reduction half reaction or oxygen oxidation half reactions. There are also other things like we've studied molecular aggregates, but I will not touch this. It's a separate topic here. Okay, so this is a very, very brief introduction into the field. So now let us consider different types of spectra. So here you can I've classified them in two groups. So this frequency domain ones. Photon in, photon out, gamma is for photon, or photon in, electron out, if we are dealing with ionization, out ionization. And for photon in, photon out, okay, there is no photon out in this process, but simplest photon in process is just absorption, so-called X-ray absorption spectrum, SAS, briefly. So, and it can be very easily studied. So if we have energies of states, if we have transition dipoles between them, so from the ground state to the I call it intermediate state, mediated by the dipole moment operator. So we have the spectrum. And despite of its simplicity, it's very powerful because, as I mentioned already, so X-ray spectroscopy is a study of local electronic properties, and we can focus on one type of atom, like transition metal in a complex, and study how environment is influencing on it. So here our joint work with Professor Hilal. So it's cobalt, different types of cobalt complexes as coexisting in a solution, in the aqueous solution of cobalt chloride. And one can see, so, okay, there is an experimental, again, lost my mouse, yeah. There is an experimental spectrum here. Experimentally, it's difficult to disentangle different species which are coexisting there. But theoretically, we can compute and we can see so how the fine structure of the bands here is changing when we change the ligands. And this is remarkable because cobalt and water, not cobalt, chloride and water, so they are similar in the ligand field strength. So it's not like ligands which are very far from each other in spectrochemical series. And we can still see the difference. Important thing here is that you see here two groups of bands, one and the second one. So, and the splitting between them is due to spin orbit coupling. So you can see how strong is it, so that it splits the bands that far away from each other. Yeah, and of course one has to take this into account. Another example of application of X-ray spectroscopy, but this time time resolved, is this operanda type of spectroscopies. When we look at the photocatalytic water splitting, and there is a photosensitizer iridium-based complex, and it has the following simplified structure. So iridium is in oxidation state 3. Deep iridium ligand is neutral, and when light comes in, so there happen some very fast processes which experimentalists cannot resolve. But finally, we end up in a iridium and 4+ state, and deep iridium ligand is reduced, so an electron is transferred from iridium to ligand. So, and later comes another region which kind of sacrifices an electron to the system, and iridium is again reduced to 3+, and the ligand stays in its reduced state. And this can be nicely seen in using X-ray spectroscopies. We can follow the oxidation state of iridium atom in the center. So originally, we see before anything happens in the ground state, we see transitions from 2p orbitals, which are lying much below the slide, so they are very deep, to the unoccupied d-like orbitals. They are sigma star in this case, but they contain a lot of d character. So, and we see this in experiment. So this line is due to these excitations to these orbitals. But as soon as we create a hole, so we transfer an electron to the ligand, from metal to ligand, we create a hole here, and a 2p electron can be excited and fill this hole. And we see an additional signal here due to this hole, which disappears when iridium gets again into the state 3+. So this is very convenient thing to follow the oxidation state as one of illustrations. Another type of spectra, as I mentioned, are electronic Raman type things, or resonant inelastic X-ray scattering. Here, everything is conceptually similar to absorption spectrum. We just need to combine two dipole moments, transition dipole moments, for the excitation from ground state to the intermediate state, from here to here, and back from the intermediate state to valence manifold, not necessarily back to the ground state, like how it's called, relay line. It can be to other electronic states, so for making Stokes or anti-Stokes lines, in analogy to Raman spectroscopy. But this is inherently a 2D spectroscopy, because we have incoming photon, we have outgoing photon. So which you can see here. So this is from work together with Mahmoud. So and Professor Hellmann was also there. So we see here the incoming photon energy, outgoing photon energy, and there are plenty of peaks here, so they are not that well seen in 2D graph, but they contain a wealth of information about electronic structure. And if we look a bit more into detail, yeah, so one can make cuts through this 2D spectra, not to analyze this complicated structure at one time. So we make cuts, and they are depicted here in the center. There is one interesting peculiarity here, is that due to very strong spin-orbit coupling in the core-excited states, we can see spin-forbidden transitions. So let me describe the mechanism of it. So valence states, for them, spin-orbit coupling is not that strong. So that's why we have states of a particular spin, like singlet, triplet, quintet, so and they are not mixing with each other much. But as soon as we go to highly excited points, so they start to strongly interact, and there are no singlets, triplets anymore, so they are not pure, so they are mixed. But what does this mean? So this means that if we start from a ground state with spin S, we go to a mixed state, and we can return back to the spin S state. Right? And this corresponds, if we look at the cuts, at different excitation energies. So this is the absorption spectrum, and we excite at different energies here. We will see, okay, some structure here due to this S mixed S transitions. And for example, this doublet of peaks, it corresponds to the ligand field splitting. So this classical thing from coordination chemistry. But since the excited state, core excited state, is mixed, we can change spin on the fly. So we can also start from S spin, go to mixed, and to S +1 or -1. And with this, we have a direct access to the spin forbidden transitions, which is mediated by this very strong spin orbit coupling in core excited states. So that's why we can not only follow the geometrical structure of complexes, their oxidation state, but we also can easily follow spin. So this is also a remarkable thing about it. Yeah, so yeah, the time is coming. So let me briefly describe photon in electron out spectroscopies. So the simplest one is when we consider the two bound systems with n electrons and n-1, and a free electron, which is liberated from the system. So this is this type of spectra, photoelectron ones. They are very similar to X-ray absorption and how they are described. So we again have a Fermi's golden rule. So we have a ground state with n electrons. So and dipole transition to the final state where the ion n-1 electron ionic state is this one, and it's multiplied by a state of a free electron, continuum electron with momentum k. Another type of process is when we just not ionizing directly from the ground state, for example, but we first excite to the core excited state, and it's very unstable, as I explained. So it decays also by emission of an electron, and it goes back to the ionized valence manifold. So this can be also described by a similar thing as a photoelectron spectrum, but just the operator here mediating this transition is essentially a two-electron part of the electronic Hamiltonian. So this is Auger process. And usually in quantum chemistry, we deal with localized Gaussian or square integrable functions. And from this viewpoint, this photon in electron out spectroscopy is a disaster, because we have continuum function, which is not square integrable, so which is oscillating up to infinity, so it's never decays really. And yeah, so it's difficult first of all to obtain these functions, and to get these matrix elements to obtain integrals is also a challenge. And as usual in quantum chemistry, one calculates matrix elements as the integrals between orbitals times some transition matrix object. And in this case, for photoelectron spectra, so for one electron operator like dipole, or for Auger electron spectroscopy for two electron operators, so it looks like this. So, and this density matrix like objects, they are different from what we used to in usual spectroscopies. So they have an odd number of creation and annihilation operators here. But as I said, so difficult is to calculate this phi k and to integrate, to obtain this integral. This bound part, which I denoted in blue color here, it's easier to compute. And sometimes people completely avoid computing continuum functions. So in this case, one just uses this blue counterpart, computes the norm of the so-called Dyson orbital or Dyson density, and obtains the intensities of transitions. This is called sudden approximation for TESS and population analysis for Auger. But in principle, one can build a full hierarchy of, as you can see here, hierarchy of approximation. So let me explain what does this mean. So usually approximation is connected to a potential. So when we ionize an electron, there is an attractive potential of ion. So, and depending how we approximate this potential, we might have an easy or inaccurate way of obtaining spectra or very accurate way. Of course, one can say, okay, we neglect this potential completely. So V is equal to 0 or is equal to some model analytic potential, like usual central symmetric Coulomb potential. Unfortunately, in this case, for many systems, one can't obtain reliable results. But what one can do, so we can say, okay, we will do a bit better than this, but not take completely complicated potential. We can say we take a potential of particular atom, so neglecting all other atoms. So this is so-called one-center approximation. So when, for example, having this complex, iron complex here, we just take the continuum as if there were only one iron atom and no other atoms. Or one can also make a spherical average of potential. So this concentric spheres here, so they denote the smeared charge of hydrogen atoms or oxygen atoms or iron inside. So this works very well for Auger spectrum because their electrons have a very high kinetic energies. And this why this is good. So we can refrain from solving a full 3D Schrödinger equation. You can just solve a radial one and make use of the spherical symmetry. And for high kinetic energies, this works fine. As you can see here, it's an Auger spectrum for NO2 molecule. So it's a radical multi-configurational molecule in the ground state even. So that's why we took this, not a transition metal, but this one. But one can see so that apart from those bands which are marked by arrows and which are stemming from different types of process, so not Auger one, so one can see a very nice agreement with experiment for both one-center approximation and spherically averaged potential. So this means that for high kinetic energies this works fine. But for low kinetic energies, of course, we need to take the full multi-centered potential. I don't want to stop very much here, so because it's a topic of a separate lecture, probably even two. So here one has to obtain this full photoelectron wave, which is not spherical, which is somewhat complicated. One has to take into account this full molecular potential, electrostatic potential, which you can see here. It's for water molecule. And this one has to do if one is interested in, as I said, low kinetic energies. or when one is interested how the intensity is varying. So this is a cross section. So essentially the intensity is a probability of ionization varying with the photon energy, or when one is interested in the spatial dependence of ionization probability. Just as here, you can see a TCDA molecule depicted here, which is sitting on the surface. And when we shine light on it, the probability that electron will come in different directions is different. And you can see here an experiment. So when it comes in different directions, and the simplistic models where we completely have no signal here in this part. So it's just don't come in these directions at all. So, and if one applies more elaborate approach, so then one sees here some probability for it. So that's why it can be especially important for oriented molecules or molecules attached to the surfaces or membranes, probably, if you find this interesting. So, yeah, so this is all about this frequency domain things. Very briefly about time domain. So, and about some, how to say, so the working horse which we are using. Here, the idea is to use as much as possible from the static quantum chemistry. So we do usual RAS-SCF, RAS-PT2 calculation. We obtain energies, we obtain different matrix elements between states. And we use this information to build our Hamiltonian. So, for example, we can include, so this H0 here contains all this information from static thing. So, but what is time dependent is the external perturbation due to external electromagnetic field. So we shine light on it, so we disturb our system and starts to react on it. And with this, one can describe different types of processes, and in particular, the Hamiltonian can look like this. So this one example where I have, I can lost my mouse, just a second. Yeah. So here I have separated the state or blocks of states with high spin and low spin. And this submatrices here, subblocks, they describe correlation, related motion of electrons, then spin orbit coupling between different spins, and interaction with external field. So this E of t is a field, and we have dipole coupling to this field. And we have put everything, so we're not solving here the time-dependent Schrödinger equation. We are solving Liouville von Neumann equation, but it's just the same, apart from the fact that we are not propagating wave function in time, but density matrix. And why we prefer density matrix? Because it's very flexible, probably most flexible approach. It can describe both completely coherent dynamics, incoherent dynamics, and all processes in between. So, and as I said, so this is implementing, or many of the things are implemented in open molcast. But what we can get from it, from density matrix, we can get diagonal elements. They are describing populations of our states. But more importantly, we can compute from it any observable. And of course, most important observable is dipole moment for us, because it's involved in different types of spectroscopic or generation of spectroscopic signals. And with this method, one can study nonlinear spectra, charge dynamics, spin dynamics. Very brief explanations. So sorry for this, that it takes that long. So one can study, for example, linear spectra in time domain. So not only in the frequency domain as before, I described before, but we shine light. So here you can see the gray envelope of the pulse. So it's very, very fastly oscillating. And this is just this envelope of these oscillations. And in blue, the response of the dipole moment. So how the dipole moment of system reacts on these oscillations of the field. So it's also like you see only the envelope, so it's very fastly oscillating here in between. And if we do a Fourier transform of this dipole moment, we obtain a spectrum. It's in nice agreement with the static spectrum and experiment. Nothing very, very fascinating here, so but it was an important test for us. But what's important, what's new or I think intriguing here, is that one can generate highly nonlinear signals like this high harmonic generation. So here is an example of H2 molecule. Yeah, very huge chemical system. Okay, but physicists, so for physicists, this is a huge system. So, but one can describe quite some physics here, which is happening. So interesting one. So we see here the field. So it's a gray line oscillating here, and the response of dipole moment. So it's not yet that squeezed as on the left panel. Okay, again, lost my mouse. As on the left panel, so we see how it oscillates, and the more the field triggers our system, the less sinusoidal is this response of the dipole. We start to see some wiggles, and if we do Fourier transform of this dipole oscillation, so we will see a high harmonic spectrum, so that our fundamental light energy is 1.55 eV. So and then we add like 2, 4. Okay, in this case, I think 1, 3, 7, and so on, 5, 7 of these harmonics, and generate a very high frequency light. So this is a process which can be studied with this. Of course, one can study charge dynamics. There is a very interesting process which is called charge migration. It's just imagine so that when you ionize a molecule and your pulse is very broad in frequency domain, so that you are incorporating or exciting, triggering many transitions, ionization transitions, then one can ionize an electron locally, not just from the full molecule, but from some part of it. And in this case, I illustrated this on the example of iodoacetylene, where iodine atom is ionized, whereas CCH moiety stays unionized. But since this local state is not an eigenstate of our system, of our Hamiltonian, it is not stationary, it evolves in time, and the charge is migrating from iodine to CCH, back to iodine, and so forth. So here we can see the populations of orbitals. So these red ones, they correspond to iodine, green ones to CCH. So you can see so that they are oscillating like this. So it goes from iodine to CCH and so forth. But the whole is also changing its spin. So as you can see from solid and dashed lines, so these are correspond to spin up and spin down of this whole traveling through the molecule. Yeah, it's one thing. So the other thing is spin dynamics. Yeah, I will not stop very much on this, but this is a nice, very brief comment. So this is a nice illustration of how strong is spin orbit coupling in four excited states. So you can see here the valence states and core excited states with no spin orbit coupling or with spin orbit coupling. And what happens, and the color corresponds to their multiplicity. So blue color corresponds to triplets, red color to quintets. And what happens with the valence states if we switch on spin orbit coupling? Not that much. So one can see, okay, probably here near crossings, one can see some differences, but they are not that pronounced. But for core states, so if we switch spin orbit coupling, so we will have no quintet or triplets anymore, we will have mixed ones. So this yellow and green colors, they correspond to states of mixed multiplicities. And if we excite, if we involve these states here in the green area here, then we will have a very fastly changing spin. So it's much faster than is usual in this intersystem crossing or spin crossover. So it can happen on the order of attoseconds. And this is due to the very strong spin orbit coupling in the core excited states. Yeah, so here are some examples. So you can see so that for some systems we can very quickly change from for this titanium system from singlet to triplet and singlet again. So and you see so it happens on sub-femtosecond timescale. Okay, I will not stop on other aspects here. Yeah, so this is an overview. I don't have any conclusions, so I just try to illustrate in which sense this theory can be applied to interpret different spectroscopic experiments. What kind of experiments are available there, so if you have any interest in any idea, so how this or that can be studied using this type of spectra, of this types of methods, so you're very welcome. As I mentioned, open MOLCAS is open. The open in open MOLCAS means that it's open source, so you are very welcome to download and install it. So I wish to help you if you have some interest in this. With this, I would like to thank my subgroup. Okay, these are actually people from Rostock. Some of them already left the group. Some of them continue. And I would like also to thank collaborations within Germany and also abroad. So like you can see here the collaboration with Professor Hilal with Professor Aziz. And with this, I would like to thank you for your attention.